Okay, good afternoon, everyone. Now we are going to discuss the reactions involving the cleavage of CO bond. Okay, so the last reaction that comes under this category is oxidation. Okay, oxidation reaction. I told you about the cleavage, right? Two hydrogen atoms will be removed from this compound. So this oxidation is also considered as dehydrogenation reaction. Then depending upon the different reagents used, the different products will be obtained. Always these alcohols will oxidize to aldehydes or ketones, then aldehydes or ketones to carboxylic acid. Okay. Then we can directly obtain this carboxylic acid from alcohol using suitable reagent. Then sometimes we can stop the reaction where the aldehyde or ketone will be obtained. So we are moving to different reactions based on oxidation. Here you can see this is the common reaction take place in alcohol on oxidation. RCH2OH, that is alcohol. Okay, alcohol on oxidation, aldehyde will be obtained. Aldehyde will be obtained. Then on further oxidation, carboxylic acid will be obtained. Okay, so this is the common chemical reaction take place in the case of alcohol. When we are using certain strong oxidizing agents such as acidified potassium permanganate, that is KMnO4. Okay, acidified potassium permanganate, that is KMnO4. Carboxylic acid will be obtained from alcohols directly. When we are using strong oxidizing agent like acidified potassium permanganate, so we can directly obtain carboxylic acid from alcohol without going through the step of formation of aldehyde. And this CrO3, okay, CrO3, that is chromic anhydride. Using this chromic anhydride, this isolation of aldehydes also possible. We can stop the reaction in aldehydes without going into carboxylic acid. So using KMnO4, directly the carboxylic acid is obtained. Then using CrO3, we can oxidize this alcohol only to aldehyde without going further oxidation. So depending upon the reagents used, the products will be different. If potassium permanganate is used, we can obtain directly carboxylic acid. If CrO3 is used, aldehyde will be obtained. And another better reagent for the oxidation of primary alcohols to aldehydes in good yield. Here also, the aldehyde will be obtained on oxidation. On good yield, we will use PCC. PCC. Its full name, pyridinium chlorochromate. Pyridinium chlorochromate. That is known as PCC. Clear, children? Pyridinium chlorochromate. Its full form is PCC. So it's a complex of chromium trioxide with pyridine and HCl. It's a complex of chromium trioxide with pyridine and HCl. They all are together known as PCC. Clear? Chromium trioxide, pyridine, then HCl. The complex of all these compounds together, it is known as pyridinium chlorochromate. In short, we will write PCC. So, using this PCC as the reagent for the oxidation of alcohols, the aldehyde will be obtained in a good yield. Aldehyde will be obtained in a good yield. These all things about the primary alcohol. Okay, only in the case of primary alcohol, these all reactions take place. Then we are moving to secondary alcohol. The secondary alcohols will give ketones. Primary alcohol will give aldehyde on reaction with CrO3, and the secondary alcohol will give ketones. Here you can see the reaction. This is the secondary alcohol because the OH group is attached to the carbon where two other substituents are there. That's why it is known as secondary alcohol. It will react with CrO3, chromic anhydride to form ketone. Primary alcohol, aldehyde, secondary alcohol, ketone. This is clear, children? Normally, in the case of oxidation of alcohols, alcohols will be converted to aldehydes, then aldehydes to ketones. Okay, that's the process. But sometimes we can also directly obtain carboxylic acid when we are using the reagent potassium permanganate, KMnO4. And we can stop the reaction in aldehyde using another reagent, CrO3. And to obtain this aldehyde in good yield, we will use the another reagent PCC. Okay. Then the secondary alcohols can be converted to ketones on reaction with CrO3, that is chromic anhydride. Is this clear? All of you? Any doubt, children? Nothing, right? All of you, please switch on your videos. Okay, then before this, in the case of tertiary alcohols, they normally do not undergo oxidation reaction. Okay, the case of tertiary alcohol, they will not undergo oxidation reaction. But in certain conditions, under strong reaction conditions and strong oxidizing agent, tertiary alcohols do not undergo oxidation. But under certain conditions, that means stronger oxidizing agents, then high temperature, etc., sometimes the reaction will be occurred. High temperature, then strong oxidizing agent. Reaction occurs, and this tertiary alcohol, it will be formed a mixture of carboxylic acid. Tertiary alcohol will form a mixture of carboxylic acid with the number of carbon atom less than the parent atom. Mixture of carboxylic acid with the number of carbon atom less than parent atom. Okay. So tertiary alcohols, they normally do not undergo oxidation reaction. Then at certain drastic conditions, that means high temperature, strong oxidizing agent, etc., sometimes the reaction will occur, and on oxidation, a mixture of carboxylic acids will be obtained. And in this mixture of carboxylic acid, their number of carbon atom will be less than the parent atom. Clear, children? That's about tertiary alcohols. Have we completed? Shall I move to next one? Yes. Then the remaining oxidation reaction. This is also another oxidizing reaction. Here the reagent used is copper vapors. When this alcohol, it is passed through copper, primary, secondary, and tertiary. Primary, secondary, and tertiary alcohol vapors are passed over heated copper at 573 Kelvin. Different products will be obtained. In the case of primary alcohol, aldehyde will be obtained. Okay, aldehyde will be obtained. And in the case of secondary alcohol, ketone will be obtained. And in the case of tertiary alcohol, alkene will be obtained. Here the same reagent is used. Okay, heated copper at 573 Kelvin. In the third case, the dehydrogenation take place. Dehydrogenation. Sorry, in the first and second case, dehydrogenation, and in the third one, dehydration. That means water molecule will be removed. That's why alkene is formed. The first two cases, dehydrogenation. I told you this oxidation, otherwise known as dehydrogenation, right? Because two hydrogen atoms will be removed. So that's about catalytic dehydrogenation. That's about the oxidation reaction. So this is the last reaction that comes under the reactions involving the cleavage of CO bond. So we have learned two types of reaction in the case of alcohols, right? Reactions involving the cleavage of OH bond, then reactions involving the cleavage of CO bond. This is clear, children? Then the next section, that's about the reactions of phenols. Reactions of phenols. Here, there are 5 reactions. First one is about electrophilic aromatic substitution reaction. Okay. the reactions of phenol. First one is electrophilic aromatic substitution reaction or electrophilic substitution reaction. Here it takes place in one aromatic compound. That's why it is electrophilic aromatic substitution reaction. Second one is Kolb's reaction. Third one, Riemer-Tiemann reaction. Then fourth one with zinc metal, and fifth one is oxidation. So these are the 5 reactions that comes under the reactions of phenol. So we are going to start with electrophilic substitution reaction. Okay, electrophilic substitution reaction, and we are starting with nitration. There are different types of electrophilic substitution reaction. Nitration is there, halogenation, sulfonation, etc. In this portion, you can learn nitration and halogenation. So first one is nitration. So before moving to this nitration, you have to learn the things about electrophilic substitution reaction. You know that electrophile, that's the electron rich, that is electron deficient species, and they need electron rich species, right? That is electrophile, and they will always attack in the position where electron is rich. And in the case of this phenol, it has one OH group in the aromatic ring, isn't it? One OH group in the aromatic ring. This OH group, it has a tendency. All of you switch on your videos. Switch on your videos, children. So this OH group in phenol, that means OH group in this aromatic ring, it has a tendency to direct all the incoming electrophiles to ortho and para positions. Okay, so the substitution will only occur at ortho and para position. Clear, children? This OH group present in the aromatic ring, they have a tendency to direct the incoming electrophile to ortho and para positions. So the electrophilic substitution reaction only take place at ortho and para positions. Clear? Then you look at this example of nitration. Here the reagent used is dilute HNO3. Phenol, it will react with dilute HNO3, and this on nitration NO2 group will be substituted, right? It will be substituted at ortho and para position. So the two products obtained, ortho nitrophenol and para nitrophenol. There is no change in the position of OH group. It will direct the incoming electrophile to attack only at ortho and para positions. Ortho and para positions. That's why the products obtained is ortho nitrophenol and para nitrophenol. A mixture of ortho nitrophenol and para nitrophenol will be obtained. So in this case, there are two types of phenols, right? So we are separating both this ortho nitrophenol and para nitrophenol using steam distillation. Using steam distillation, we will separate the two products using steam distillation. And the reason is that when you look at the bonding between this ortho nitrophenol and para nitrophenol, here in the case of ortho nitrophenol, intramolecular hydrogen bonding is there. Intramolecular hydrogen bonding. What's the meaning of intramolecular hydrogen bonding? That means bonding within the molecule itself. Hydrogen bonding within the molecule itself. Here you can see the NO2 group and OH group. Within the same molecule, the hydrogen of OH group and the oxygen of NO2 group, they will form a intramolecular hydrogen bonding. Okay, intramolecular hydrogen bonding. Then you look at the positions of hydrogen bonding that occurs in para nitrophenol. Here, one oxygen atom of nitro group in the one para nitrophenol, it will hydrogen bond with other molecule, right? Oxygen present in one molecule of para nitrophenol, it will form hydrogen bond with the hydrogen of another para nitrophenol. So here it is intermolecular hydrogen bonding. First case it is intramolecular, and the second case it is intermolecular hydrogen bonding. So this ortho nitrophenol, it is steam volatile. That means it will be easily converted to the form of vapors. Okay. It is steam volatile due to intramolecular hydrogen bonding. And this para-nitrophenol, it is less volatile. So using steam distillation, we can easily separate these two mixtures. Both products will be obtained, orthonitrophenol and para-nitrophenol. In the case of orthonitrophenol, the hydrogen bonding is within this molecule itself. That's why it is known as intramolecular hydrogen bonding. Okay, so it will be easy to convert to the form of vapors on heating. But in the case of para-nitrophenol, it will form hydrogen bonding with other molecules. That means the bond between these molecules will be very strong. So it is less volatile. So it is very difficult to convert it into the form of vapors and escape. In the first case, it is within the molecule itself. So it's easily converted to the form of vapors. That is, it's considered as steam volatile. And in para-nitrophenol, it is between the molecules. So it is difficult to break that bond and convert to the form of vapors. That's why it is considered as less volatile. So due to the difference in their reaction with this conversion of vapors, we are using this method, steam distillation. Clear, children? Steam distillation is the method used to separate these two mixtures, orthonitrophenol and para-nitrophenol. So when you heard this electrophilic aromatic substitution reaction in phenol, always the substitution take place in ortho and para position, not in meta position. So the incoming electrophile will be occupy the ortho and para position. And the separation of these two mixtures, it occurs by steam distillation. And the reason is that intramolecular hydrogen bonding in orthonitrophenol and intermolecular hydrogen bonding in para-nitrophenol. This is clear? Children, any doubt? Okay, in these two cases, we are using dilute HNO3. Dilute HNO3, right? Dilute nitric acid will be used. If we are using concentrated nitric acid, then another product will be obtained. If we are using concentrated nitric acid, this substitution occurs at all ortho and para positions. This two ortho positions and one para position, it is substituted by this nitro group. And this IUPAC name is 2,4,6-trinitrophenol. 2,4,6-trinitrophenol. Its common name is picric acid. Okay. When we are using concentrated nitric acid instead of dilute nitric acid, 2, 4, 6 positions are substituted by nitro group and it is known as 2,4,6-trinitrophenol. The common name is picric acid. Common name is picric acid. But here the yield of reaction product is very poor. Very small amount of product will be obtained. So the main method of producing this picric acid, first we convert this phenol into, phenol will treat it with sulfuric acid. This is the actual method of manufacturing of picric acid. Phenol plus concentrated sulfuric acid. Okay, phenol plus concentrated sulfuric acid. It will forms phenol 2,4-disulfonic acid. This product will be obtained. First, we convert this phenol on reaction with concentrated H2SO4 to phenol 2,4-disulfonic acid. Then later, it will react with nitric acid, concentrated nitric acid, and the product will be formed 2,4,6-trinitrophenol. Okay. So this is the actual method of preparation of picric acid, because the reason is that during the direct conversion of phenol into picric acid, the yield is very poor. Only small amount of product will be obtained. That's the reason. And this trinitrophenol, picric acid, is considered as a strong acid because 3 NO2 groups are present. This NO2 groups have a tendency to withdraw electrons. So it will be more powerful in acidic property. That's why. Clear, children? This is considered as a strong acid. Reason is that NO2 group is present here. 3 NO2 groups are present. They will withdraw electrons from this molecule and it will be more positively charged. That means they can able to donate more H plus ions. That's why it is considered as a strong acid. That's about nitration. Have we completed this one? Yes. Then one more thing, that's halogenation. It's also similar one, only in the change in the reagents. Here bromine in CS2. CS2 is carbon disulfide. So here same phenol molecule, only the change in reagents. Bromine in carbon disulfide. CS2, that is carbon disulfide. That is the reagent used. Here also para-bromophenol and ortho-bromophenol will be obtained. Para is the major product. Either carbon disulfide, that is CS2, or you can also use chloroform, CHCl3. They are considered as the low polar solvents. Okay, solvents with low polarity or low polar solvents. Carbon disulfide and chloroform, low polar solvents. So this reaction take place in the presence of low polar solvents, carbon disulfide or chloroform. So the reaction of phenol with bromine in the presence of carbon disulfide, para-bromophenol and ortho-bromophenol will be obtained. That means the substitution occurs at ortho and para position. And this para-bromophenol is considered as the major product. And here the reaction take place at 273 Kelvin. That means low temperature. Low temperature. So low polar solvents and low temperature is favorable for this chemical reaction to take place. And again, this phenol is treated with bromine water. 2,4,6 tribromophenol will be obtained. That means all the ortho and para positions will be substituted by this bromine. Okay, phenol, it will react with bromine to form 2,4,6 tribromophenol. All the ortho and para positions will be substituted by bromine. So here the main difference with the halogenation of benzene and this phenol. In the case of benzene, it will take place in the presence of Lewis acid. Okay, in the case of benzene, this halogenation will take place in the presence of Lewis acid. But in the case of phenols, this polarization of bromine molecule take place in the absence of Lewis acid. So you can note this point also. In benzene, halogenation take place in the presence of Lewis acid. But in the case of phenol, it's not needed. Halogenation take place in the absence of Lewis acid. It is due to the highly effective group that present in this phenol, that is OH group. Halogenation occurs without Lewis acid. Reason is that OH group present in the ring. Okay. So that's about the two types of substitution reaction, electrophilic aromatic substitution. First one is nitration and the second one is halogenation. Then we can discuss the remaining things in the next class. I think within 2 periods, this chapter will be completed. Some commercially important alcohols, the next portion that is deleted. Okay. Then after the reactions, we are moving to ethers. Then one more chapter left, that is P block elements. So according to the instructions from the school, I think the portions will be completed within September 15th. Okay, so there will be more periods for chemistry till September 15th. So all of you please cooperate with that. After that, we can start the revision. Okay, children? Okay, then thank you all. See you in the next class. Bye.